Chapter 2, slides 1 through 6. Now we're going to start focusing a little bit more on some details that I very quickly went over in Chapter 1 review. We spent a lot of Chapter 1 talking about bond trends. And I need you to really know those bond trends because this will help you in drawing structures the way that typical organic chemists draw structures. We draw structures using bond line format. Bond line format allows us to see a little bit clearer, without the mess, what the interesting and functional parts of a molecule are. Now I want you to remember that we covered the fact that a carbon-hydrogen bond and a carbon-carbon bond don't really have polarity to them, right? There's not one atom in a carbon-carbon bond that is very polar, right? Because they're sharing the electrons equally between them. And the difference in electronegativity between a carbon and a hydrogen is practically nothing. So both of these carbon-carbon and carbon-hydrogens, these bonds are both very nonpolar. So what? Well, nonpolar bonds mean that one atom is not necessarily more electronegative or more electropositive than the other. And if you remember, reactions, which is what we're really after here, reactivity and reactions won't occur unless there is a different distribution of electron density, right? Negatives are attracted to positives. That's when chemistry happens. So if we don't have anything particularly negative or positive about a carbon-hydrogen bond or a carbon-carbon bond, they're considered nonpolar and thus not really where a lot of action is happening when it comes to reactivity. Atoms like sulfur, oxygen, phosphorus, nitrogen, chlorine, bromine, iodine, the ones way to the right on the periodic table, are the ones that have more electronegativity and therefore more susceptible to being in a relationship with another atom that is going to lend to being a polar bond. A polar bond is what we're more interested in because that's where all the functioning is happening. That's where all the reactivity is going to occur. So, bond line structures allow us to look at really big hairy molecules in a way that highlights the reactive areas. So, I'm interested in carbons. Obviously, I'm an organic chemist, but I'm really not that interested in the carbons and hydrogens that are ultimately creating the infrastructure or the scaffolding that hold up the reactive areas. So if you look at the two molecules that I've drawn on this slide, they're actually the same molecule. The one on the left, what do you think about it? I mean, doesn't it look hairy? It's kind of hard to wade through it and see what's actually interesting there. If we distill it down to a bond line structure drawing on the right, what pops out are those interesting areas. There's an oxygen, a nitrogen. They're so much easier to see, aren't they? All these lines that we drew in between are really representing carbons and hydrogens. So the bond line structure is much easier to read, and it's actually easier to draw. You don't have to keep drawing all these bonds to hydrogen. It seems a little difficult to read at first, but trust me, you will get the hang of it. And what is very important to make a smooth transition to bond line structures is to have solidly in your pocket an understanding of bond trends. If you understand bond trends, this will become very easy. Okay, using the same structure as the previous slide. We're still going to be using lines to represent bonds. So that's the similarity that we see with Lewis structures. Things that are different though, differences. The big differences is that we don't draw carbon, and we don't draw hydrogens on carbon. We do draw hydrogens, but only when they're not on carbon. All of the hydrogens that are on carbon are not drawn. Also, we don't draw lone pairs. Oof. Again, they're there, but we expect you to know the bond trend. Oxygen's bond trend is 2 bonds, 2 lone pairs. So the oxygen far to the right, you gotta assume that those 2 lone pairs are indeed there. We just didn't draw them. Nitrogen, 3 bonds, 1 lone pair. The nitrogen, as shown up at the top here, has the 2 hydrogens and 1 bond to the scaffold. So 3 bonds are shown, but the lone pair is assumed. Okay, so those are the things that are the major differences with Lewis dot structures. One of the nice things is that because we're not drawing the carbons, we are using a zigzag representation to show those carbons. Okay, and the nice thing about using a zigzag is that it actually reflects or mirrors the tetrahedral nature of an sp3 carbon. So remember that the angle for an sp3 hybridized carbon is about 109 degrees. And when you do these zigzags to represent carbons, you're actually drawing a very close relationship to that 109 degrees. And I'll show you a little bit more about that later. So how do we do this? How do we not draw carbons and hydrogens but know that they're there? Well, we use the ends and bends system, and this works most of the time. I'll show you the exception in the next slide. So what you're going to do is you're going to represent carbons by ends of a line and bends of a line. So if you look at the molecule far to the left here, every end of the line, so you can see this, the end of the line is a carbon. We just didn't draw it. There's a carbon there. The next bend in that line is a carbon, and the next bend is a carbon. The next bend is a carbon, and the end is a carbon. Now, because there was no charge, right? I didn't draw any negatives or positives on the molecule. Therefore, the molecule is assumed to be neutral. Therefore, all of the bond trends need to be met. Carbon's bond trend is 4 bonds. So all of the assumed bonds to make up the octet that carbon needs to be neutral, we are going to assume that it's filled by invisible hydrogens. They're there. We're just not drawing them because we don't want to make our molecule look very hairy. I mean, which molecule would you rather look at? The one on the left or the one on the right? As time goes on, you're going to find that the one on the right is so much easier to read because you're not harrying it up with hydrogens. When you do ends and bends, it's important to understand that those are carbons there, and sometimes it's super helpful to just number them so that you don't get lost. And it's okay in the beginning as you're learning to draw these bond line structures to maybe add the hydrogens in when necessary. For instance, if that highlighted green carbon was pointed to on an exam or a quiz, and you were asked, what's the hybridization of that carbon? It's totally fine to draw in the assumed hydrogens. Why? Because if you're moving quickly and you look at that carbon and you say, okay, I'm going to draw the carbon in. There's the carbon. And I ask you for the hybridization or the geometry. A lot of students will say, oh, it's bent, right? But that's not the case here. Carbon doesn't have 2 bonds. It has 2 more hydrogens off of it that are assumed. Therefore, there are 4 electron domains, right, or electron clouds around it. And the way to orient 4 electron clouds around is sp3 tetrahedral. Not bent. So by not understanding that there's 2 hydrogens there assumed, you may get led to sp linear or bent because you're just looking at the carbon and it's in what looks like a bent shape, and actually get it wrong. So it's okay to, if you're pointing at one specific atom asking for its hybridization, to draw in, as time goes on, but you'll get there. You won't have to do this as we move forward. So a good thing to do is often to just draw out the numbers, like number the carbons, kind of like an accounting, right? If you're an accountant, you're keeping track of everything. What's going on? So if the atoms are omitted, how will we know how many atoms are attached to each carbon? Quite simply, what we talked about last chapter, the octet rule. You got to know your bond trends. Bond trends are going to help us. Hey, these 3 molecules do not have a charge attributed to them. Therefore, I can make very quick assumptions about each carbon. I can number my carbons. I can say how many carbons are in each of these molecules. 1, 2, 3, 4, 5, 6. So there's 6 carbons. This is a C6 molecule. How many hydrogens? Let me see. Carbon 1 has to have an octet. So carbon 1 only has a bond to carbon 2. Therefore, it must have 3 assumed hydrogens. Carbon 2 is attached to carbon 1 and carbon 3. That's 2 bonds, so it must have 2 assumed hydrogens. Carbon 3, 2 assumed hydrogens. Carbon 4, 2 assumed hydrogens. Carbon 5, 2 assumed hydrogens. And carbon 6 only has 1 shown bond, so it must have 3 assumed hydrogens. Count up the hydrogens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. That's H14. Try the other 2. What you'll notice is that the second one is also C6, H14. The last, C6, H14. What you'll notice about these is that they're all the same quote unquote Lego pieces. I gave you 6 carbons and 14 hydrogens, but they're connected to each other very differently. If I take away the hydrogens here, because again, boy, does that really hurry up our molecule. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. 5 isn't connected to 6. 6 is connected to 2. That's weird. How about this one? 1, 2, 3, 4. Oh, 5 is down here and 6 is over here. They're completely connected differently. This is what we call isomers. Same molecular formula, different connectivity. These are different molecules with different properties. We're going to learn a little bit more about them later. Let's get back to orientation ends and bends rule. I mentioned that there is one example that doesn't follow the geometry, and that's when we're talking about triple bonds. When you're doing single bonds to carbon, even double bonds with carbon, the zigzag shape actually is a pretty decent way of looking at the geometry, because what you're not seeing, let's say if I was looking at the carbon highlighting right here, remember that carbon is sp3 tetrahedral. Okay? That means that we see the 2 bonds, and those 2 bonds are in the plane of the paper. There's a hydrogen assumed, and that's coming out at us. And another hydrogen assumed, and that's going away from us. Even though we could draw 2 hydrogens using sticks, that would look very flat. That would look very square planar. But understand tetrahedral has 2 bonds in the plane of the paper, and then 2 bonds, one coming out at us and one going away. You can actually make this shape in 2 different ways using your hands. This is fine for tetrahedral. Even for sp2 carbons, that carbon is sp2, it only has one assumed hydrogen off of it because it's got a double bond. This is trigonal planar. And therefore, you can see that all three, the double bond and the two single bonds, are in a triangle, and they're all in the plane of the paper. So the zigzag works just great again. The zigzag doesn't work when you're talking about a carbon involved in sp hybridization. Why? Sp hybridization is linear. I do not want to draw carbons in a zigzag when the two carbons share a triple bond. That looks weird because linear, or sp hybridization, implies 180 degrees. So we want to make sure that our bond is 180 degrees. So you can see that the only time we don't want to do carbon zigzags is when you have a triple bond. So a critical skill for you guys is to really practice understanding how to interpret bond line structures and also how to draw them and what their meanings are. Never draw carbon with more than 4 bonds. We are all guilty of doing this from time to time because we're working too quickly, but you know your bond trends. Carbon cannot exceed its octet. And so sometimes when you're assuming hydrogens and you're trying to draw them in for yourself to figure something out, you know, you might go, oh, here's a carbon. Oh, there's a hydrogen here. No, there's not a hydrogen there, right? The carbon, as drawn, already had 4 bonds. You just drew a 5th bond. So you're going to get some stuff wrong there. So don't move too quickly. Take your time, but really learn the skill and trust the fact that you will get better and faster at interpreting it. Bond line structures, again, help us to see the carbon infrastructure, the scaffolding that holds together the interesting functional groups that we're going to be talking about. So you can see in this molecule, ooh, there's a sulfur hydrogen there and a chlorine and some double and triple bonds. It makes life so much easier to see when you can see where all the reactive parts of the molecule are. So for practice, you guys can try and write the chemical formula for this molecule. How many carbons are there? How many hydrogens are there? Right? How many sulfurs? How many chlorines? Write those in. See if you can write the chemical formula for this. I'd also like you to get some more practice by labeling the hybridized atoms in the structure. What's the hybridization for that sulfur? Right? What's the hybridization for that carbon? For every hybridized atom, tell me if it's sp, sp2, sp3. Okay, so heteroatoms are the atoms that are not carbon and hydrogen. So this is an organic chemist's world. A heteroatom like sulfur or chlorine or oxygen, those atoms are called heteroatoms. We do not assume hydrogens on heteroatoms. So remember, when I have a hydrogen on sulfur, I draw that hydrogen. When I have, if I go back to this molecule here, I had a hydrogen on an oxygen, right? Hydrogens on oxygens. I draw them in. Hydrogens on nitrogens, I draw them in. Okay? Do not assume hydrogens on heteroatoms. You only assume hydrogens on carbons. The last thing to talk about is conformational rotations. Now, if you look at these two molecules drawn in their bond line structures below, you'll notice that they look different. Are they different molecules? In the previous slide, we talked about isomers. Same molecular formula, different connectivity. Let's take a look at these. Carbon 1, 2, 3, 4, 5. I can draw a straight shot, 1, 2, 3, 4, 5. Without picking up my pen, I can draw the 1, 2, 3, 4, 5 zigzag. And then there's an extra carbon off of 3. We'll call it carbon 6. How about the one to the right? 1, 2, 3, 4, 5. Without picking up my pen, I can draw 1, 2, 3, 4, 5. And then there's an extra carbon off of 6. These are drawn differently, but they actually have the same connectivity. They have the same number of carbons and hydrogens if you do them out, but they look different. However, if you really kind of count it out, they're actually connected the same way. In fact, I could draw another conformation for this molecule. One, 2, 3, 4, 5 without picking up my pen. And then 6 is off of 3. Now, what is this all about? These are not true isomers, right? They're not constitutional isomers. I didn't change their connectivity, but I drew them conformationally different. So these are all the same molecule represented in different orientations, different conformations. Think about yourself. I'm me. I can stand up, and I can sit down, and I can lay down, right? I am still me. In order for me to go from standing to sitting, you do not have to break your legs and reattach them to your body, right? There is no bond breaking. You're not changing yourself. You're still you. You're just bending and rotating your hips, right? As you sit down and to change your conformation. Molecules are not stagnant. They are twisting and bending and conforming into different shapes without changing who they are or what they are, right? They are still that molecule with the same properties, but they can rotate. Single bonds, single bonds are made up of sigma bonds, right? Single bonds are sigma bonds. This means that you've got head-on overlap, like a barrel, like they're just that sigma bond, the overlap of the two orbitals. There is rotation around a single bond. So every single bond can rotate. Any one of these can rotate. Even the carbon-hydrogen bond can rotate. It's just a single sigma bond. Free rotation exists among all single bonds, so they can orient however. Now that's to say, some conformations are lower in energy than others. I know that when I'm lying down, that's my lowest energy state. Sitting up is better than standing up, so that's the next lowest in energy. And then my highest energy conformation for myself is standing up. Molecules are no different. Sitting, standing, laying down, one of its conformations is probably more lower in energy than others, and it exists in that state because of its low energy more often than the others. So conformational analysis is something we're going to look at, but I want you to be aware that all single bonds rotate. Bond line structure practice. I'd like for you to draw bond line representations for 3 isomers. Remember, connected differently. I'm giving you the Lego pieces, 5 carbons, 9 hydrogens, a chlorine, and an oxygen. I want you to construct them in 3 different ways where all of their octets and bond trends are met. 3 possible isomers for that C5H9ClO. I'd also like for you to take the molecule written here, CH2CH, C2,4CH3. See if you can convert that to a bond line structure. And then, once you've got a good bond line structure for this molecule written out, I'd like you to draw 2 more rotational conformations. Make the molecule look different, but keep it the same molecule, just by rotating a single bond.